I work with data from epilepsy patients, especially patients that are candidate to resection surgery. So there are about 65 million people with epilepsy in the world. 2/3 of these respond well to drugs. That is, they become seizure-free after they're in a drug regime. 1/3 is not responsive to drugs. Of that 1/3, about 20% go to surgery, which is you try to remove where the epileptogenic focus is on the brain. And of those that go into surgery, only 60% are seizure-free. We're talking about a whole 4 million people worldwide that go into resection surgery. So if you haven't seen it, it's something kind of like this. There's a more picturesque kind of cases, which is for patients, pediatric patients, which you have to perform a surgery called hemispherectomy, which is you remove a whole hemisphere of the brain. And the amazing thing about this is they can have some normal development after that. They can learn how to read and graduate school and everything with only half of the brain. But usually we're talking about removing part of the temporal lobe or the hippocampus, which is the most common type of epilepsy, temporal lobe sclerosis. So the primary tool of diagnosing epilepsy is the EEG, so squiggly lines, which get very squiggly whenever you have a seizure. The thing is, as Klaus mentioned yesterday, you can always expect a patient to have a seizure when you're measuring it. So what happens is physicians look for these. These are interictal epileptiform discharges, which are very common in the signal when you have a patient with a severe case of epilepsy. And they do visual detection of these patterns here, which is a very difficult process. We work with data from patients that had their EEG taken inside the MRI scanner. That has a lot of noise introduced into it because you're talking about changing magnetic fields, and that changes the potentials that are measured in your EEG electrodes. So we have to do some signal processing, which involves these steps, which is average artifact subtraction. We average out channel-wise the artifact from our EEG machine and the blood flow as well, because blood flow inside the magnetic field generates a potential as well, so that makes things a little bit harder. We have some standard stuff, bandpass and notch filters to remove grid frequency, etc. But we do independent component analysis, which is kind of a primitive machine learning type of way to remove components that might be related to eye blinks or other stuff like that. And mostly we do re-referencing, which, I mean, what I did most was to explore different types of referencing to our connectivity patterns. Working with data, this project I'm presenting here is with data from 10 patients. It uses 63 electrodes. Referencing was a reference point in the middle of the cranium. So it is this FCZ electrode. We also have one ECG to monitor their heart frequency. And they had a very high acquisition rate at the beginning, then we downsampled to 250 hertz. The thing about our data is they have the squiggly lines marked at the IDs, the events that we're looking for. So these are all physician notations. So here is at the point of a starting pattern, and every line here is going to be one of these patterns. What I try to do is to make a way all of this is dependent on visually marked notations. I tried to see if we can use a connectivity pattern to make it easier to find those notations, have some other kind of marker. So the technique I used is called Motif Synchronization. We have our time series, which is this. And we take all the patterns 3-point configuration can make. So you have 3 points. They can be 3 points going up, 3 points going down, anything in the middle. And for each time point, we look at the specific time point and the ones that are following it. And we change that for a pattern, for which of these patterns it was. So that way, instead of having a series that's codified into amplitude, we have a series that's codified into patterns of amplitude. There's a difference. And what we do now is we compare point by point. If they're equal for 2 different time series, then we have a 1. If they're different, we have a 0. And we look at how these patterns repeat at different lag values. If we look at a window here, so let's say I have a window of 5 samples. We look at a window that's at the same point and with some lag in front of it and see which one holds the most correspondences between them. Then for that window, our maximum, we have a coefficient for our connectivity, which is going to be this guy, and that directionality, which is if a pattern happened here first and was repeated here, then it's going to be an arrow from here to there. And with all of that, we can make a time-varying graph. So for each time step, we have a different graph, right? The parameters we used were 20 samples, time windows, sliding window, and there was a threshold of 90%. So for every window, 18 out of 20 samples needed to be a match for there to be an edge. We looked at lag values from 1 to 3 samples. We removed the 0 because of this. In the brain, we have a thing called volume conduction, which is whenever we measure an EEG signal, you're not only measuring the fields, the local fields that are right under your electrode. You're measuring information from the whole brain. Because it is an electromagnetic field, it's going to vanish with the square of the distance. And it propagates almost instantaneously at the speed of light. So all events that are simultaneous on our EEG acquisitions, they can be related to volume conduction. And I wanted to show a little difference because between what we're looking for propagating depolarizations, which is how neuron activity spreads instead of the electric fields, how it spreads. So there's a short clip from a movie here. It's the beginning of Fight Club, but it's gonna make a noise. I intended it for to wake you up. And it happened. Oh. Okay, we're not gonna do it again. But the idea was to wake you up. I think it worked. But it's just how neuron depolarizations travel inside of a neural network. And other than that, lag, we explore different referencing techniques. What is standard to do is you have your EEG that was referenced with respect to an electrode. So it's electrical potential. It's always measured in reference to something. If we take a reference to a central electrode, we usually get something called channel drift. That is, our reference might change. It might be associated current to it as well. So a standard thing to do is to try and remove this channel drift that is associated with our signals with some type of average. We usually do a common average reference, which is take all of your signals from all your channels, average it, and then subtract that average from every single channel. But the thing is, when you have something like a spike or some spiking region of the brain. What happens is the red one's going to be our reference to the mean, right? Average reference. If there's a big dip here, this guy shifts your mean. So wherever you didn't have a spike before, which is the original reference is the green line here, you're going to have a little dip. This relates to, probably can say this is a referencing artifact. And the thing is, when we look at our connectivity patterns, so this would be our original reference, and we can see that's much clearer in these two cases. But when we are using the mean reference, there's also some connectivity on the other side, which does not relate to what we're looking. When we reference to the median, however, it's much more restricted to where this event happened. So this would be a spike on the left hemisphere. In that way, we can, so this is an EEG with two marked events here, and we can see that each marked event has a kind of clustered graph associated with it. So this is event on the right side, and this event on the left side. And we take a look at the number of edges that happen during the signal. We can see it goes up whenever we have one of the events we're looking for. So you have a cluster associated with this type of event. And when we sum all of these time-varying graphs in one dimension, we have this static network. So this would be the static network for the whole graph. And this would be for all events, and here separating events on the right side and left side. This is for one patient. This is going to be for another patient, which is the same thing. But we are looking at the connectivity matrix for this patient. This is asymmetrical. We have edges going from one electrode to the other. But it translates very well to where the interictal spikes were found in the EEG. We also have the edge weight distribution, which is in log scale. So we can see that out of all possible edges we have on this guy, the edges with the highest value are only a few, and they are associated with the region where we find the epileptogenic focus. We have this result for 9 out of our 10 patients. It translated well to the electrodes in which we found the EEG activity. That patient had on the right and left side would be this one. And also, if we look at the distributions of, if I go back here a little bit, distributions of this guy, the orange line here, the average, the moving average, we can see that for the clustering coefficient of our networks, it was slightly higher for events in almost all cases as well. We have these two here, but we have more outliers here on the downside for non-event epochs. And that's the main result I wanted to show you. There are some other things I did, which is for seizure data, which is not from our data. Some of it was I did while I was at Newcastle University, but I don't have access to that data anymore. But I have this, which I think I can show you. So this is from seizure data. So you have 120 seconds before the seizure, then the seizure starts, and then 120 seconds after the seizure. So for this collection, it was an intracranial EEG, and the seizure started at a very focal place. Like you had 2 spiking electrodes. That would be a very type of focal seizure. Then it spreads out a little bit more for the whole network. And we can see right at the point where this happens, this transition for focal seizure to a more spread seizure, the number of edges in our networks explodes. which is very nice. And also for scalp data, this is using an open data set from Temple University. Well, you can count how many seizures there was here. So I think that's very clear. Some references as well, and these are all from our group and collaborators. These are some other important readings, I think. And these are all the people I wanted to thank. My advisor, she's a drawing. People from Unicamp, Professor Fernando Sendes, which is the neurologist at the head of the Brain Institute. Bruno Campos, the physicist at the lab that works with those guys as well. Marina Alvin, the physician that marked all the epochs on the EEG. These are the people I met during my time in Newcastle University last year. I was a visiting researcher there for 6 months, and this is Professor Garcia, who helped me with the motif synchronization technique. That's all. Thank you very much.
Thank you. Any questions?
Thank you, Leonardo, for this interesting approach. My question is about the first part, the detection, the network associated to the interictal spikes. Did you work only on the market spikes, or was kind of...
No, this result here, this is the whole network. This is all
yes, my question is that you estimated the network only on the segments indicated by the clinicians?
No.
So
this, that's what I wanted to show you. This is the... So this is very important because I think that's the great part about our research. This is not for the segments that were marked. This is for the whole EG we acquired the whole time. So this would be 5 minutes of data.
Okay, perfect. Thank you.
Any other questions? Okay, so thank you, Leonardo.
Thank you.
And we'll have a coffee break now, and then we come back for the last part of the workshop.